Hey everyone, and welcome to The Explainer. If you're a focused learner aiming to absolutely crush your Cambridge 9709 mathematics exams, you have logged into the exact right terminal. Today, we're taking a completely different approach. We're going to treat complex mechanics problems like an algorithm that can be solved with code like syntax. We're acting as system architects to master two fundamental yet completely misunderstood concepts. First, gravitational potential energy, that's dependent on mass, gravity, and height, or MGH. And second, kinetic energy, driven by mass and velocity, half mv squared. Look, we aren't just going to memorize these formulas like rote data. We're going to learn how to deploy them logically, line by line, to secure those top A-star marks.
Okay, let's look at the command matrix for today. 6 core modules. We'll start with the A-star difference, load up the core mathematical principles, build out our 5-step framework, unlock the method mark strategy, debug the system with the top 3 examiner warnings, and finally, install a memory hack for exam day. Let's run it. Starting with Section 1, the A-star difference. We really need to address the high stakes here, specifically the massive performance gap between settling for a B and achieving that elite A-star in Cambridge math.
So consider this pivotal question. Why do incredibly smart, capable students find applying these energy concepts to unfamiliar contexts so incredibly hard? It's like a system crash. You might know your MGH and half mv squared syntax inside out, but the absolute second the exam paper presents a scenario or a physical environment you've never seen before, your brain throws an error code and panic sets in. Why does that happen?
The root cause is actually outlined right here in this powerful quote from a Cambridge senior examiner, basically the lead admin of the grading system. They state that the difference between a B and an A-star often comes down to how well you truly understand gravitational potential energy and kinetic energy. The crucial takeaway, the gap isn't about your raw memory capacity or hard-coding equations, it's about deep structural comprehension. It's knowing the why and the how the system works, not just what the formula is.
That brings us right into Section 2, core mathematical principles. We literally have to upgrade our mindset here. You have to move beyond looking at MGH and kinetic energy as static strings of text and start treating them as dynamic, versatile tools in your analytical toolkit. Look at how the syllabus targets two entirely different cognitive domains. On the left side, we have basic knowledge and understanding. That's just recognizing the formulas exist. It's basic data entry. But the right side? Application and analysis. This is where the top-tier marks live. The examiners are running a stress test on your ability to apply structured, logical reasoning to physical contexts you have literally never encountered before.
To clear the examiner firewall, your mindset must prioritize analytical depth over superficial breadth. The grading system explicitly rewards students who exhibit a connected, conceptual understanding. Think of a roller coaster cresting a steep hill. A top student doesn't just plug numbers blindly. They draw on evidence-based reasoning to mathematically prove exactly how kinetic energy transforms into potential energy and vice versa, dynamically as the state of the system changes.
So how do we actually execute that in a high-pressure exam setting without crashing? Let's move to Section 3, the 5-step framework. This is your procedural methodology. Think of it as a foolproof step-by-step algorithm to attack any energy, work, and power problem. Here is your base code. Step 1, deconstruct the question. Parse the prompt and break it into logical parts. Step 2, extract relevant data. Pull those variables, the masses, heights, and velocities, out of the text and define them. Step 3, select your analytical framework. This is the logic gate where you decide, am I using conservation of energy here or the work energy principle? Step 4, execute with clear notation. Run the math cleanly. And Step 5, present with correct terminology. Print your final output with justified recommendations. By running this exact systematic sequence, you are proving your architectural depth to the examiner.
Now, before we compile this next patch to secure maximum marks, optimize your system feed. Subscribe to Ace the Exams right now at Ace the Exams and turn on all notifications for weekly system updates. Okay, let's get into Section 4, the method mark strategy. This is a massive paradigm shift in how you view the grading matrix.
You absolutely have to understand the concept of a method mark. These are points awarded for proving your analytical process and explicitly showing you're working out. And here's the kicker. You get these even if your final calculation at the very end is completely wrong because of a silly calculator typo. The examiner is rewarding your logical sequence and your syntax, not just the final printed output. Look at how this plays out in the real world. In column 1, you have the wrong final answer, but you meticulously documented your working out line by line. Method marks literally save your grade. You still get points. But look at the second scenario. Wrong final answer, and you showed 0 working out, you get absolutely 0 marks. The system rejects it entirely. Never, ever skip writing down your intermediate logic steps.
Let's pivot slightly and run some debugging in Section 5, Top 3 Examiner Warnings. We've pulled these critical, fatal errors directly from Cambridge Principal Examiner reports. Consider this your map to avoid tripping the system's alarms. Here is the #1 most common syntax error that students make year after year. It stems from rushing your inputs, and it caps your maximum score instantly.
Using the wrong approach for the wrong context. Listen, you cannot mindlessly copy-paste MGH or half MV squared without pausing to evaluate the specific physical environment of the question. Is there friction? Is there an external driving force? If you apply a basic closed-loop conservation formula to a system that is actively leaking energy to heat, that is a fatal logic error. Context dictates the algorithm you choose. Moving on to the second major bug to patch. This one is entirely preventable, yet it catches out even the most mathematically gifted coders simply because they ignore the platform rules.
Forgetting to check your format and presentation. This isn't just about making your math look pretty for the sake of it. Proper headings, appropriate mathematical formats, and clear sequential annotations are strict conventions in the Cambridge 9709 mainframe. If the examiner cannot clearly read your logic loops because your presentation is spaghetti code, you will bleed marks. And that brings us to the third and final warning, pulled straight from the examiner's source code. This is the ultimate hurdle that separates decent outputs from flawless ones. Answers that are not specific to the context given. When a multi-part question asks you to evaluate a complex scenario and print a conclusion, your final justified recommendations must explicitly relate back to the unique prompt. You cannot just return a hard-coded, generic textbook answer at the A-level. Your final statement must call the specific variables of the exact problem you just solved. Let's initialize our final section and see how all this builds into a deployable tool. Section 6, the memory hack. How do you pull all this up from memory when the exam clock is ticking down? I want you to install this cheat sheet architecture into your brain right now. The acronym is DESEP, DESEP. Deconstruct, extract, select, execute, present. Whenever you face a terrifying, unfamiliar energy or power question, write DESEP at the top of your page like a startup script. It will instantly force your mind to run the correct procedural loop and prevent your system from panicking. Your next step is deployment. Go grab a past paper, find a high-tariff energy and power question, and run the DESEP algorithm. If you want more high-level system upgrades, make sure you subscribe to Ace the Exams at Ace the Exams. Hit the bell and leave a comment below with your specific subject and level so we can optimize our next masterclasses for you. I'm going to leave you with this final, provocative thought to process before your next exam. When you log in and sit down in that hall, are you going to act like a script kiddie, just passively memorizing formulas and hoping for an easy prompt? Or are you going to use the architecture we built today to actively prove your analytical depth to the examiner? The choice is completely yours. Happy studying, and I will see you in the next explainer.